Okay, maybe we should start. Hi, everybody. So last time on Tuesday we talked about neural networks, right? And we talked about the fact that neural networks are very expressive, meaning that if you have a neural network and you want to represent a function, you can pretty much do that, right? For any function. If your neural network is deep enough, right, and you have enough neurons. And then it turns out that with depth, it's getting just, showing everything. As you go deeper and deeper, you get exponentially more and more powerful, which practically it means you are capable of doing a lot of things by a neural network, right? So that was what we talked about last time. And now here you have this neural network. This is capable of making any function, right? And then if you think about whatever we have done since very beginning of this course, we have always tried to just represent a function, right? So there was a function which was looking at the data and then shows us the cluster. There was a function which was looking at the data and was trying to just reduce the dimensionality. There was a function which was looking at the data and was telling us what is the label. There was a function which was looking at the data, and again, it was giving us the label, but this time the label could be real valued in the regression, right? Predict, for example, the price or something. So anything that we have done up to this point is pretty much just implementing a function. And we try to somehow come up with a sort of parameterized function, which we can set the function first, and then we can find out the weights, right? And here, this is the same thing going on. So for the neural network, you have, again, a parameterized function, right? And what are the parameters inside the neural network? Those weights and biases for every single neuron that you have, right? So the key point is that you should always think about the neural network as a box, and then this box has a kind of tuning knob on it, right? And then when you change this knob, the weights are changing, and by changing the weights, you're changing the function inside the box, right? And now the universal approximation theorem is telling you that, well, it is a huge sort of cases for this box because this is capable of presenting anything that you want, right? So that is the key idea. So expressive power, we talked about it. As we go deeper, it gets exponentially more and more powerful. And because of that, we expect that if we can make one neural network or tune the weights inside a neural network properly, we can do any job that we have. Now, today what we want to do, today and next Tuesday, we're going to talk about this, how we can deploy a neural network, meaning that how you can build one neural network, how you can use it to do one specific learning task, and definitely you need to tune those weights, right? This is what we call the training, and how we can do the training. Okay? So we're going to get an overall understanding of how we can use the neural networks, basically how we can design it to make the right inference. This is the first job we need to do. And secondly, now that we have the right transition from the input to the output that we want, how we can train the weights in order to get the performance or the behavior that we want inside the neural network. So now, let's look at this guy, and since up to this point we always talked about the hypothesis and the class of function and things like this, maybe it would be better if we just put everything inside a box. So this is a neural network. It has a bunch of inputs. It has a bunch of hidden layers. These are the green layers here. And then you have an output layer, right? The input goes inside the hidden layer. It got processed over and over, and then finally at the very output you have a bunch of representation. These guys here, right, are giving you the features that you want, right? And then out of that feature you do the last layer, which is basically either a linear regression or linear classification, right? And out of that you get what you want. Now these neurons, obviously they could have also a bunch of biases. That's not really important. The important thing for us is that how we can think about it as a box, and I can just put everything inside this neural network into a box, right? And this box is describing a function which is connecting the d-dimensional input that I have to the output, right? Before this, inside the box, there was always one matrix, right? A set of weights. It was the linear model, right? You get your inputs, you multiply them with a bunch of weights, maybe you add them, and then you get your output. There was a linear regression model, right? Or maybe you do some other operation before you check, like, for example, in the binary classification, right? No, this box is getting more weights. It's getting more complicated. But it's still, this box, whole of it, is just a function, right? Now, this box is parameterized by a bunch of weights, which I'm showing by W, and you do know what are those weights, right? The weights and biases of every single neuron you have here, right? If you collect all of them into one set, this is the set of weights that you have. This is the knob that I talked about. Like, if you change them, you're changing the knob, right? And the function is getting changed. And what you want to just change it so that you're going to perfectly match your data, right? For instance, you see that your data, the samples that you have are looking like this. Now you want to play with this knob so that the function passes through those points, right? Everybody's cool? Good. So we can put it back into, for instance, supervised learning framework that we had. The data samples are a bunch of labeled data samples, so we already know where the inputs are and how the output should look like. And now we are just setting a hypothesis, right? The hypothesis is that X is connected to any input that I have is connected to the corresponding label using a model FW, right? So there are a bunch of weights that if I set my weights inside the neural network to be them, then this is going to connect the input to output properly, right? This is the assumption that you're doing now. Now, considering this assumption as compared to the linear models, which one is a stronger assumption? The stronger assumption, I don't mean which one is more powerful. I'm talking about which one is less realistic. Linear model is less realistic, right? There's no reason. Most of the things you see in the nature are not linearly related, right? So there's no reason for them to be linear. But this one is not that strong anymore, especially if the neural network is deep enough, right? Because the universal approximation tells us if that is deep enough, that's probably a right assumption. Well, it's not an assumption anymore, it's a fact, right? Okay, so that is going to be your hypothesis set. So the hypothesis set is now the set of functions which are described by that neural network. And we know that this is huge. And finally, the thing that we want to design a learning algorithm. It means that we're going to get this neural network, we're going to get our data, and then we want to just make one algorithm so that we design the parameters inside this neural network to match the data we have, right? Now, since I'm talking about supervised learning, what kind of algorithm that should be? Sorry? For classification, for instance, what is the learning algorithm that we talked about? Maximum likelihood you can tell, or risk minimization, right? We are basically, again, going to do risk minimization or maximum likelihood as before, but this time, instead of thinking about the linear model, you can think about neural network, right? Everybody's cool? So the formulation is not going to change. So I could start again from very beginning, like clustering, and I can keep on going, doing this time everything by a neural network, right? And you should be able to follow all of it. The only difference is that when I end up with solving the optimization problem, which is supposed to give me the right choice of the weights, then probably there start to be some sort of trouble, right? Because the optimization is not probably anymore very trivial, right? So this is the only difference, but whatever we have done up to this point is exactly the same, right? So the thing that I want to do it for supervised learning because, I mean, if you want to get one thing about neural network, that's probably the best thing. But you can always extend it to the unsupervised learning as well. So, yeah, let's start with one case. And the first thing I want to talk about is about inference. And to do that, let me first focus on the classification problem. When we talk about classification, this means that the labels that we have are discrete, right? we have a few labels, few classes, right? And the sample that you have, X, is either belonging to class 1, class 2, to class K, right? One of them. And then what do you want? You want to build one neural network, and you might fill it with whatever you want inside, right? But the input should take your right input, d-dimensional input, and the output should be somehow that you can infer one of the K classes, right? Everybody's cool? Yeah? Now, that's what we want to do, and what we can do, we can, for instance, be a bit naive, and if we want to be naive, we could say like, okay, I put this neural network to look like this. It has K different outputs, okay? And each time something goes in, one of them just fire. The rest of them are 0, right? Then you're going to say this is the class, right? But if you start doing it, going all over the optimization problem, other things, you end up understanding that this is pretty much not a good choice, because it's going to make us lots of troubles. This is very, it's like basically just doing the hard classification with in the binary case, like you just use a step function to decide the class, right? A better choice is that we go ahead again with a probabilistic approach and we think about probability, right? If we think that way, first of all, we can do maximum likelihood. Secondly, we are going to work with numbers which are real valued. It's going to make the life much easier. So a better way of thinking about it is that we think about the neural network. To get this X, right? X is the input, is for instance the image that you want to classify. And then it's going to give you one probability, something between 0 and 1, right? And that probability is telling you what is the chance of this particular X belonging to class I, for instance. Okay? Everybody's cool? So we did it before, if you remember, when we did logistic regression, right? When we had logistic regression, we put a sigmoid there, and we can again do it here. We put a sigmoid at the output. This is going to compute as a probability, and then we treat that output as the chance of our input belong to class 1, right? Then the chance of our input belong to class 0 is 1 minus that guy, right? Everybody's cool? Yep. Okay, so that's what you can do. Now, this guy, this F, this neural network, what is it modeling? Any idea? Obviously, it's a distribution. It's a density, right? But what kind of density is it? What kind of distribution? Is it probability of X? Is it the distribution of X input? No. What is it? Distribution of the label given X, right? So it's a conditional distribution, right? So you're saying what is the was a heavy lecture. So that F, the neural network, is essentially computing for you the distribution of your label V given the X input that you have to your neural network, right? This is what it is modeling, right? And to model this, it's getting a bunch of parameters. These are the weights of your neural network, right? And now you want to just play with that it gives you the right distribution, right? Now, what is the ultimate thing that you would like this to look like? What kind of distribution you would like this guy to look like? If I give you X, how do you like your label to be distributed once you know X? If I show you image of a cat, what would you like to be the distribution of the label between cat and the label is, for instance, cat or dog? Not Gaussian. Why Gaussian? No, but think about this. I give you X. I show you the image. What is the distribution of label? It's 1, 0, right? It should be cat 1, dog 0, right? So you want it to be one-hot representation. You want it to be strictly the one you want. It's not always the case, right? If I show you one very bad quality image, you might be unclear about whether it's a cat or dog, right? And this is when you are not happy with that image, right? But at the end of the day, you would like this guy. It's a categorical distribution. It's not a continuous distribution, right? You want it to be 1 on the right label, 0 anywhere else, right? Or if it's not exactly the case, roughly approximating that, right? Okay, so that's what you're going to do. So let's think about the binary classification, for instance. You have one image. The image is cat or dog. And then you're going to give it to your neural network, right? And then this guy is going to pass through multiple layers. So the pixels first get multiplied with a bunch of weights. Added up with some biases, you have a bunch of features. You activate them, right? Again, you repeat this, you activate them. And you keep on doing till you get into a bunch of few features at the very end, right? And then you would say these features must say whether it's a cat or dog, right? So you're going to get those features. Again, you do a linear operation on it. And then you can put here some function, some activation function, which is going to compute you a probability, right? For example, if you put a sigmoid here, this y is a number between 0 and 1, right? And then you would say if that number is essentially the chance on the board, the chance of label being dog given the image that I have, and the chance of label being cat is simply 1 minus that guy, right? Correct? Now, for the moment, assume that I have done some magic and I do know what are the right choices of the weights here. So I put all the weights correctly, right? Now, if I put one dog image here, then what do you expect to see here as the value of y? Almost 1, right? Or very, very high value, right? But what happens in practice is that I give it a bunch of dogs. For some of them, it's very close to 1. For some of them, it's not exactly 1 or close to 1, right? Maybe 0.7, 0.6. What do you do at the end of the day? How do you conclude out of your observation from the output? For example, if y is 0.7, what do you say about the image? It's likely to be dog, right? So you still give the chance to be dog, right? Because the probability is more than half, right? So it means that the chance of being dog is more than the chance of being cat. So you're going to conclude dog, right? So this process is what we call an inference. Inference means that you put the image in, or data at the beginning, right? It's going to pass all over your neural network or whatever the model is, right? And you see the output, and from the output you conclude what is your prediction of the label. Of course, you cannot guarantee 100% that you are right, but that value here is going to give you a bit of idea also. I mean, if you interpret it as a probability, it's going to give you a bit of idea about how confident you should be, right? If it is 0.7, then it's likely to be dog, but you are not super confident. But if it's 0.95, then you would say, okay, I'm pretty confident this is a dog, right? As long as the neural network has been trained well. So I have not tuned the knob very properly. Okay, everybody's cool? Question? No question? Okay, great. Now, how can we do it? Obviously, we can use a sigmoid. So this means that whatever I get in the last hidden layer here, I am going to just do one linear operation by one single neuron here, right? So one linear operation, a bunch of weights get multiplied to those features. And then I add a bias, right? This number that I get at the output, this original z calculation computation that I have done here, this z is a real valued number, right? It could be something very negative, very positive, right? But you want it to be between 0 and 1 because you want a probability, right? And what you're going to do, you're going to put z inside a sigmoid, and this is going to give you a probability, right? And you can treat the other guy 1 minus this one, right? So the other guy would be the probability of class 1 is exactly what comes out of your neural network, the output of the last sigmoid in your neural network. And the probability of the class 2, the other class, is simply 1 minus what you see at the output of your neural network, right? So this is the typical way that you're going to use neural network when you want to do classification, right? And now you might say that, yeah, obviously you're going to take the class which has the higher probability, but now you might tell me what's going to happen if instead of instead of a binary classification, I have a multi-class classification. For example, I have 10 classes or so. Yes? Here?
Which function do you use, right?
Yes, but yeah. What?
Oh, okay, well.
Okay. No worries. No worries. Yeah. So now, if we have multi-class classification, first of all, say for example, I have 4 different classes, right? And I want to again put a neural network, a model, which is going to tell me some information about the class, right? A good way of doing it, again, is to just go for a distribution, right? But this distribution here that I have is on the label given image, right? What kind of distribution is it? I mean, it's still a categorical distribution, right? Because my labels could be either class 1, right, for instance, class 2, and so on, till how many classes, C class you have, C different classes, right? Now, you want to have some numbers here, which are the probability of each class, right? So you want your neural network to give you C different numbers, and these numbers must be describing a distribution, right? Everybody's cool? Okay, how we can do this? Well, so we basically want to have, for example, oh, I said here C, sorry, I put it K, because on the board it's K on this slide. So I say I have K different classes, right? I want to get at the output of my neural network K different numbers, and these numbers should be probability, right? It means that they should be non-negative, right? And they cannot exceed 1, so they are numbers between 0 and 1, right? Any other property they need to have? Sum up to 1, right? So you want them to sum up to 1, right? Now, any idea how we can do it? We had it in the previous lectures. I didn't explain it in the lecture. I told you you can take a look if you do. Yeah. You can use softmax, right? So you can use a function which does a bunch of computation and at the end does nonlinear operation which has this property. And the most famous one that we know is the softmax function. But you can come up with your own function, even though nobody nowadays does anything but softmax. So how we can do it? Again, once we are over with all the hidden layers, you have a bunch of features, right? And now the thing is that you want to get K different numbers, all of them describing a distribution, right? So you can get a weight matrix and you multiply it by the features that you have. Obviously, the number of columns you have on W, it should be the size of your feature, right? The number of columns you have in your matrix should be size of your feature because every row is going to get multiplied with the features, right? And the number of rows you want is K, right? It should be K, the number of classes, right? So you should treat every single entry inside Z as a computation specified for one class, right? Everybody's cool? You see that? Now, next thing, the Z values, even though you have K different scores, for instance, K different numbers, values for your K different classes, they are not yet describing a distribution, right? They could be very positive, very negative, right? You want them to be between 0 and 1 and add up to 1. And the way that you can do it, you can use this operation softmax. Now, how does the softmax work? It's going to get every single z, and it's going to compute an exponential function of that, right? So z1 to zk, now you compute exponential of z1 to exponential of zk. Now, exponential function, can it be negative? No, it's always above the vertical axis, right? So it's never negative. This means that the guys here in this vector, they are all non-negative, right? So this is one part of the job that we needed. The second thing, we want them to add up to 1, right? So we're going to divide all of them to their sum, right? So sum of all of these z values, exponential values, e to power z1 to e to power zk. You add all of them up, right? And you put it as a normalization factor. Now, if you do that, what's going to happen? Well, if you add up every single number in this vector, since they are all normalized by this one, this is going to add up to 1, right? Everybody's cool? Everybody's seeing that? So, moral of the story, the output of this softmax is a distribution, right, on k different classes. Yes?
So in the first one where it says k linear combinations in the output layer, does that mean that we have, it's kind of like k separate neurons that do individual linear combinations?
No, here, if you use softmax, they are not k separate neurons. You have what we call a vector activation. Because this softmax, obviously the output for the first guy also depends on all the other calculations, right?
Gotcha.
So anything in between has individual neurons. But this very output, you need to mix them, because if you don't do, then you cannot build a distribution.
Gotcha. So then for when you have the W5 plus B, that's applied to the entirety of the output of the...
Exactly, yes. So whatever you got in the last hidden layer, you have a bunch of features, right? Maybe 10, 20 features. Then say you have 10 classes, you want to do 10 class classification. Then you compute it up to your last hidden layer, 20 features. And then you get a matrix which has 20 columns and 10 rows, right? You multiply it with these features, you're going to get 10 different values. And then you pass all of them together through one softmax. And it's going to give you a 10 class distribution. And then you use that one, right? Questions? Everybody's cool? Okay. Now, softmax is basically just computing your distribution. And the reason that we call it softmax is obviously because when z is larger in the distribution, it's going to have higher distribution, right? So you can treat z calculations as a kind of a score, which are specified like if one is larger than the other one, is somehow telling you that this guy has higher probability than that one, but it's not probability yet, right? So you are transforming those scores into a probability by using softmax, right? But it's still the one which is the largest going to have the highest probability, obviously, right? Questions? Okay. Now, what about the case of regression? Well, I guess regression is much easier, right? You don't have any trouble with this last activation because you don't really want to compute this categorical distribution anymore, right? You want your output to be a real valued number, right? So this means that your very last layer could be simply a linear regression, right? You can do that. So the key point here is that your output should be a real valued number. If you have a multidimensional output, again, you need to have a real valued multidimensional output, right? But there are some tricks here as well. Sometimes you need your output to be within one specific region, right? For instance, I want the output, one of them is about the height, right? Height of a person, one of the outputs. is just representing height of someone, some person, right? And for that height, you do know that no one could have height negative, right? So you want it to be positive necessarily, right? So you need to somehow build your neural network in a way that it's gonna make your output to be positive, right? So in the regression case, it could be also the case that you are limited in the scope of the output, given the nature of the problem, right? Okay, now if you are not restricted, obvious choice that you are going to do is the linear regression, right? You're going to get your last features, and then you multiply those features with some weights, you add up a bias, this is the output you want. If you want multiple of them, then obviously W should be a matrix, B should be a vector, right? But still you can do it, right? And if you are limited in terms of like the interval that the output could be in, then you might be interested to use some sort of activation, right? For instance, if you want your output to be somewhere between -2 and 5, right? You want the output of the neural network to be a number between -2 and 5. How you can do this, you could say, okay, I first do this calculation here, and after doing the calculation, computation Z, I'm going to activate Z by sigmoid, right? Sigmoid is going to be between 0 and 1, right? And then you're going to do a transform again on this one, right? So 7y minus 2 is definitely between -2 and 5, right? This is one of the choice. Yeah? So you can play around with that output if you know the scope of the problem, but typically using a linear output is very common in this case. So everybody's cool? Yes. Sorry?
Like the type of function you use doesn't really matter because it's already nonlinear.
Which function you mean?
Like the output.
No, it doesn't matter. It doesn't matter. No, because the features have been enough nonlinear that they are just learning whatever you want, right? Okay. If you change that, once you're training, it's going to get adopted to this new architecture. Okay. The key point here is that your architecture should be able to give you the output you want.
Right. Yeah.
Right? That's it. No. No. Sure. Everybody's cool? So, well, now, once we have been okay by the inference behavior of your network, it means that you have built one neural network which is taking the input that you have and going to give you the output of the kind that you want, right? If you do that, then the next thing that you want to do is probably you want to train it. It means that now you want to somehow play with that knob to make the weight the right weight, the weight that is actually giving the output you want, right? How we can do it? Obviously, we can go ahead by empirical risk, right? And the empirical risk, what is it? We talked about it before. We said if we have one particular sample X with the label V, and we have the output Y of the neural network, then we're going to get one loss function. We are comparing these two guys, the output of the model, neural network, and the output that we want. This is a true label inside the data set. We compare them. We want their expectation to be minimized, but since we do not have the distribution, we're going to average it over the data set that we have, right? This was what we call it. We called empirical risk, right? So this is going to be the empirical risk, and this Y that we're talking here about is basically the output of our neural network, right? Now, neural network depends on all those weights inside the box, right? And this means that if I fix the weight, this expression here is fixed, right? If I fix W to be something, and if my data is the same as, I have a fixed data set, now I compute this, this is fixed, right? The only thing that let me change this guy is to play with the weights, right? Everybody seeing that? So I want to play with these weights. This is why I write the empirical risk to be a function of weights, right? So it's a function of weights. I want to minimize it with respect to weights. Same thing that we did before. I mean, back to then we had just one single neuron, right? It was a linear model. But now we have lots of them, right? Interconnected to each other. Okay, so this is going to be the way that I'm going to find the optimal weight. So it means that I want to find the best weight, W star, which is going to minimize this empirical risk, right? And you can guess if you have a deep neural network or even a shallow neural network, this function here could be very complicated, right? This is not anymore the simple quadratic function that we had for linear regression so that we easily minimize it, right? Probably we need to do one better approach. And what is that approach? What do you think? What is it? Gradient descent, right? So we definitely need to use gradient descent because this is the only algorithmic way we can minimize a function, which is so complicated, right? Okay, we're going to talk about gradient descent next time in more details. Basically, there is backpropagation that enables us to compute the gradient that we want, and out of that, we can do gradient descent, okay? Now, one thing left here that we should talk about is what's going to be the choice of this loss, right? How we can use this particular loss function. Now, what is your choice if I want to do binary classification? If I want to do binary classification, my model is going to compute one sigmoid, right? That is the probability of one of the classes, right? And now, what do you think? What would you put your loss? You see the output of your neural network, you want to compare it to the true label. Yeah? Cross entropy, this was what we did last time, right? And cross entropy is basically the negative of logarithm of the likelihood, right? If you remember. Basically, in this case of classification, it's quite easy. We want to maximize the likelihood, right? So it means that we want to minimize negative likelihood or negative log likelihood, right? So as long as we know what is the log likelihood, which we can simply compute it from the logarithm of the output, we want to minimize that guy, right? That's what we do in this case. One naive approach that people used to do initially when they developed a neural network was to think about the indicator function, meaning that they look at the output and they would say, okay, the output tells me that the class is 1, right? But the true class is 2. So here an error has happened. Error is 1. So when the output, y, is not matching what, okay, here it shouldn't be y negative if, here I'm thinking about, sorry, step function. But yeah, I think it's quite confusing for you right now. Because y here is actually my z computation before, right? So this y that I'm representing in this slide is actually z before I pass it through the sigmoid. This is the reason that, but it's not, it's a bit confusing. I should have had this again z, but yeah, sorry about that. So don't confuse yourself. This is not the activated version. Y is before activation. But anyways, the way that, like if I have my label here, as you see, when the computation is positive, the label is 1, right? And if the true label is 0, this means an error. Again, if the computation is negative, the label is 0. And if the true label is 1, then again we have an error, right? But if the computation sign and the true label are the same, then we don't have any error, right? So if you think about this kind of loss, then you can compute the empirical risk. That is going to be basically the error rate that you have. What is the fraction of time that you have error when you do classification? And you try to minimize it. This makes total sense, right? You want to be correct all the time. But this is going to make you a lot of trouble because this function is not actually differentiable. So basically you cannot use gradient descent. That is the key issue. And instead of doing that, people might think about this particular choice, y minus like the square norm, right? Or sorry, a square error. Now, do you think that if I use this one, and here, again, think about y to be even the output of your sigmoid. Y to be output of your sigmoid. if I use this loss, do you think that this is going to give me a good choice? It is going to help me find or learn the correct distribution? Yeah.
Does it only work because it's binary, so V would be 0?
Yes. Yeah. Since it is binary, it's going to work, right? So let's think about this. V is the true label, right? Say V equals by 1, okay? And then Y is the value out of your sigmoid, right? Now, if you try to minimize this, it means that you're going to make the output of your neural network after sigmoid to be as close as possible to 1, right? If V is 0, then you're going to make the output of your neural network to be as close as possible to 0, right? So it means that when the class is 1, your neural network is going to learn to give you output 1. When the class is 0, it's going to learn to give you the output 0, which is basically what you want, right? So if you think about that, you would say Y, which is the output of your neural network, and V is the true label. If you want to minimize, to make this difference small for every single sample that you have, well, you would say if V equals by 1, I'm going to get my output very small, close to 1, right? So I'm going to keep it close to 1 to make the loss as small as possible, right? And the same thing, if V equals by 0, then I try to give an output, or the neural network going to learn to give you an output which is close to 0, right? Because this is where the loss is small, right? And if you do that, it's going to still work, right? But if you do that, you're not doing maximum likelihood, obvious, right? Because you are not maximizing the likelihood, you're just minimizing the difference between your likelihood and the true label, right? Now, what if you want to maximize the likelihood? What should you use? This is what you need to use. Let's think about it. Let's say my class is 1, okay? If the class is 1, what is the probability of that class computed by my neural network? Your neural network is giving you just one value Y, right? That is the output of the sigmoid. We treat that as the probability of class 1, right? Okay, if the class is 1, the probability of class 1 is Y, right? So Y is the likelihood here, right? Everybody's cool? Now, log of this likelihood is log of Y, right? Correct? Now, you want to maximize the likelihood, so it means that you want to minimize negative log likelihood, right? So if I put the loss to be this one, now when I train my neural network or I minimize this loss, I am actually maximizing the likelihood, right? Same thing you can say in the case of V equal by 0, right? When your label is 0, then the probability computed by your neural network, well, neural network is giving you at the output the probability of class 1, right? So Y is the probability of class 1, correct? So 1 minus that Y is the probability of class 0, right? So 1 minus Y here is again the likelihood. Log of that guy is the log likelihood. You want to maximize it, so you minimize negative log likelihood, right? Everybody's cool? Questions? So, do you know what is this guy? We had it before. This is cross entropy, right? The cross entropy function, this is what we have seen before. Cross entropy is essentially the loss function when you treat your problem as a maximum likelihood. Right? Okay, so people in the computational domain, they usually do not immediately talk about maximum likelihood. What they would say, okay, the previous loss that I showed you works fine. This loss also works fine because obviously when Y is exactly the same label, right? If Y equals by 1 here in the first line, right? The loss is going to be 0, right? if y equal by 1 when label is 1, then the loss is going to be 0, right? Again, if the true label is 0 and your y is 0, what's going to happen? It's the second line, right? The true label is 0, y is 0, 1 minus 0 is going to be 1, so the loss is again 0, right? So the loss is a loss, as before. It's 0 when the labels are the same, output and the label are the same. It's going to be large when they are different, right? But the key difference here is that when you think about the amount of loss when they are not the same, you're going to see that when they are different, in cross entropy, you're going to get much larger value, right? Like in the square error that I showed you, when your label is 1 and y is 0, you're going to get at most loss 1, right? But here your loss could potentially go to infinite, right? Same thing for the other case, right? So this means that somehow cross entropy is just penalizing everything much harsher, right? And because of that, this is somehow pushing you more forward, to more towards the right distribution. But at the end of the day, why it should be a log, or specifically in this form, this is simply coming from the maximum likelihood. Because we know maximum likelihood is the best thing we can do. Questions? Yes?
So the y on this slide is the probability.
Is the probability, the output of your sigmoid.
So the y on the previous slide is computed.
Here, yes, before this I did this mistake, right? I mean, it doesn't change anything. If you, instead of putting it 0 here, make it half, okay, it's the same thing, right? So if you don't want to get confused, instead of making it 0 and talk about the sign, you just put it half here, okay? And then you can think about the output of sigmoid. Because output of sigmoid is going to be more than half when it is positive, yes, yeah, and less than half. But here I meant the, no, it's not. In this loss, it's not. It's the activated.
In this loss, the y is
the activated one.
The activated.
The output of your sigmoid, right? It's not going to impact, like, it's not going to change the whole thing, but it's going to impact seriously if you don't use sigmoid here. Because then y could be anything, right? But maybe it's better that you just think about all of them to be activated, but here instead of 0, you think about half, right? That's going to make it easier. Okay? So all of them, you always, when you are doing classification, you always compute a probability. Okay? Always. Yes.
Curious, where does like how does it relate to like cross entropy, like the name itself? Why is it that we have
because you can write this guy down as a cross entropy. Like, I'm going to show it in the next slide. Like, you can think of this cross entropy that you're computing here, the cross entropy between the distribution coming out of your neural network and a sample of your original distribution. And then when you compute the average, the empirical risk, you're basically averaging it. So this is an estimator of the cross entropy between two distributions. One of them is the data distribution, and the other one, the distribution learned by your model. Yeah? But you probably see it more clearly in the next slide. Okay? Questions? Okay, so now let's say I am doing multi-class classification. So in the multi-class classification, we had the neural network. The input goes in, you do all the calculation, k different classes, right? And then you do softmax, correct? Now at the output of softmax, you have k different outputs, right? And these are probability, right? You're going to select the one which has the highest probability to be the one is your class, right? But now, if you want to just maximize the likelihood, what do? Well, you would say the output, say, for example, the class, the true class inside your data set is 1, okay? this means that the first one is the probability that you are looking for, right? So y1, the first output, you see in this slide, I've written here yv, right? V is the class, right? yv is the probability of the class you are looking for, right? Now you want to maximize this likelihood, right? So it means that you want to maximize this y. You want to make this y close to 1, so everybody else is close to 0, right? You are going to compute log likelihood, right? And then you, instead of maximizing it, you just minimize its negative, right? Everybody's clear? So this is, again, the cross entropy in a multi-class case. Yeah? And I do know that you have seen this weird formulation, sum of something. It's exactly that guy. Let's do it together. Let's say that I got y, right? Y is the output of my softmax. It's a bunch of numbers, all of them between 0 and 1. They add up to 1, right? But my true label is this guy. And I'm showing the one-hot representation. It means that I am showing the label or the value at the correct label to be 1, at anyone else to be 0, right? For example, if my label is 1 and I have 4 different labels, I am going to show my label like this. 1, 0, 0, 0, right? This means that I'm in class 1, right? If the true class is 3, then I'm going to show it like this, right? 0, 0, 1, 0, right? Now, here the true class is V, right? So I'm going to put everybody 0. The element V is 1, right? Everybody's cool? Now, what you want inside Y, you want, let me see, oh, I don't have it as a vector. You want inside Y, everybody else be pretty much 0, only the guy which is at this location V to be 1, right? If that happens, what's going to happen for you? What would be the cross entropy? If Y is exactly this guy, what's going to happen? The cross entropy is going to be 0 because that Y at location V is 1, log of 1 is 0, right? So in this case, the cross entropy is 0, right? If they are different, if this output is not that guy, cross entropy is not 0, right? And indeed, it is larger than 0, right? So it's again a loss function as you want it. Yeah? But it's just maximizing the likelihood, right? Now, you can go ahead and write it down in this form. Like I told you, I am using this one-hot representation, right? So this is what you see by the indicator function. That is going to be 1, is a vector of the same size. It's going to be 1 only when you have your index being the true label, right? And you can write down the one that I showed you in this form, right? What's going to be the output of this summation? Well, the coefficient is 0 for any I which is not the true label, right? This coefficient indicator, right? It's going to be 1 only when I is exactly V, right? And this is going to be minus log of Y V, right? Everybody's cool? You see that? Yes.
Well, we mentioned that the Y is the output of the softmax.
Exactly.
But I thought the output of softmax is a probability value.
Is a vector of probability, is a categorical probability, right? A vector, right?
So then what happens in the cases that we don't have an exact one? Because most of the, like we will never have an exact one in that vector. It's just a probability of...
Yes, yes. It's going to get very close to 1. The remaining one's going to get very close to 0. But it's never going to get exactly 1 and exactly 0, obvious.
So then wouldn't the output of the log then, and that's like the conditional...
It's not going to be 0. It's going to be very close to 0. Yeah, I mean, if you train, you never get cross entropy absolutely 0. 10 to power. I mean, it can get as close as you want to 1, right? and then it's going to be 10 to the power minus something. I mean, the cross entropy is going to be minus something, right? 0.00001, for instance, right? And then this one, if you just interpret it in terms of log and everything, then this means that, for example, y, the output at that particular one, is 1 minus 10 to the power something super large, right? And the rest of them are pretty much 0, right? But if you want to have exactly that case also included, you need to change. Softmax cannot do it. But, I mean, you accept this because softmax is extremely smooth, right? It can make everything.
So what about the case that we haven't fully trained? So let's say our model gives out not values close to 1. It's giving out,
Some, yes,
values.
right.
So in that scenario, we're not really using cross entropy as an evaluation of the training. We're really just using it just to understand what the softmax is outputting.
No. Like next thing that we're going to do, we're going to train, right? And when we want to train, we're going to use cross entropy, right? So you pass your data, you see the label at the output. Based on the label, you compute cross entropy. When it's far away from 0, you compute the gradient, you update your weights, right? By gradient descent. And the next time when you send your image, it's going to get closer to the right. Like the value, the probability of the right class is getting higher, right? And you keep on doing this by gradient descent until it gets very close to 1. And of course, everybody else should be close to 0.
Okay.
Make sense?
Yeah.
Oops. Oh. I see. Okay. Probably. What time is it? Oh. Okay. Let me just wrap it up quickly. So, yeah. So one thing that you might notice here is that when you have this 100 representation, you can write it down in this form. So log of a bunch of probabilities times v. This v vector is again a probability vector, right? Because it's 0 everywhere, 1 at the right one, right? It is a very certain sort of probability, right? And this cross entropy that you're computing is indeed the cross entropy between those two probabilities, right? But since one of them is 1 hot, you always see one of the outputs showing up, right? That's it, right? Everybody's cool? Okay, great. So, yeah. That is, in general, the cross entropy between the two distributions, y and v. And v for us here is just a 1 hot distribution, so that's quite easy, right? Now, what about the regression case? What would you use as the loss in the regression case? I mean, obviously the difference, right? So if you have a single output, right? If you have a single scalar output, then you're going to just compute the square error between the true label and the output of your neural network. And if you have a vector, then of course you can add them up, right? So if you have multiple outputs, you can just compute the difference between each pair, and then you add it up, which is basically the second norm, right? And if you use, in this case, this loss, and you try to minimize the empirical risk, then you are basically minimizing the mean squared error, right? Because for every sample, you compute the squared error, and then the average, the empirical average expectation of that is the estimator of the mean value, right? Which is the mean squared error, right? So this is when you train by minimizing the square error or mean squared MSE. Okay, that's it. Questions? So what did we do? We basically want to somehow tune our neural network. And we first said that we need to just fix the input and output such that it gives us what we want, right? Next thing, you need to have a sort of loss function. And that loss function, you probably want to go always by maximum likelihood. But for the two cases, the two famous cases that we're going to use, you have seen that, right? So you have this loss function. Since you have the loss function, you can compute the empirical risk, right? And since you have computed the empirical risk, you have the objective to minimize if you want to train your neural network. The only thing left is that how you can really minimize that guy. And that guy could be super complicated, right? It's extremely non-convex function, which you have no closed form solution for that, right? And the only thing that we can use is the gradient descent algorithm, right? So you're going to start from some random choices of weights. You compute the gradient of the loss function, the empirical risk. And every time, you just move opposite direction of that gradient, right? If you keep on doing it for enough number of iterations, then hopefully your neural network is going to converge to something, right? But now, the big question is that how you can compute this gradient, right? And this is what backpropagation is designed for. To just use chain rule to gradually go backward on your neural network and somehow compute those gradients, partial derivatives that you want, okay? So next time on Tuesday, we're going to start from here. We're going to talk about backpropagation a bit so you get the idea. And after that, we are going to just get a bit of more details on, for example, stochastic gradient descent and those stuff, okay?